And now we will move on and do a small review about functions. So the first thing to note about functions is that functions arise whenever one quantity depends on another. So if we have the x value, which is usually called the input, and the y value, the output, depends on this x value. So now which of these two sketches down here are functions? So another thing that determines whether something is a function or not is the vertical line test. Basically, all you have to do is draw a vertical line at every point, but maybe we'll look at one vertical line for now. And in how many points in this graph does this vertical line pass? It only passes in 1 point. Now let's look at the other one on the right. I drew a vertical line. It passes in 2 points. So what we can conclude from that, if it passes in only 1 point, then it passes the vertical line test. So it is a function. However, the one on the right, it passes in 2 points. This means it does not pass the vertical line test. So it is not a function. So the vertical line test ensures that there is only one y value for a given x value. Now, let's learn a bit more about functions. So the domain of functions is all the possible x values or all the possible inputs. And the range is all the possible y values or all the possible outputs. So maybe some examples that you might know or that we talked about earlier. For 1 over x cannot be 0. So x equals to 0 is not in the domain. For square root of x has to be greater than or equals to 0. So let's say x equals to -2, this is not in the domain. Now for logarithmic functions, x has to be greater than 0. So for instance, x equals to -3, this is not in the domain. So let's look at a simple function to start with. F of x equals to 2x minus 1. Let's graph it quickly. So the graph will look, this is just a simple sketch, to look something like that. And so looking at this graph, you might notice that the domain is all real numbers because look, it can keep on getting longer and longer from both sides. So the domain is all real numbers. Same for the range, it's also all real numbers. And this is the graph on the side. Now, in order to get better at graphing, or if you're not able to graph this quickly, keep in mind that our function is f of x equals to 2x minus 1. You can plug in the point x equals to 0. When you do so, you get y equals to, or f of x equals to 2 times 0 minus 1, which is minus 1. So this point here is 0 minus 1. Now, let's solve f of x equals to 0, so 2x minus 1 equals to 0. So x is equal to 1 over 2. So this point here is 1 over 2, 0. Now let's look at another function. G of x equals to square root of x plus 2. So We agreed earlier that in a square root, what's inside the square root has to be greater than or equal to 0. So x has to be greater than or equal to -2, and that's the domain. Now for the range, let's try to graph the function and it will become clearer for us. So square root of x plus 2. We start by graphing square root of x, which looks like this. And then we shift the graph 2 units to the left. And our graph becomes like this. In a few minutes, I will be explaining to you more about shifting and how it helps us when graphing. So this is how our graph looks, and we can notice from the graph that the range is y is greater than or equal to 0. Now, let's find the domain of another function. F of x equals to ln of x minus 2 divided by x plus 3. So for ln and logs, everything inside has to be greater than 0. So x minus 2 over x plus 3 should be greater than 0. Now we draw a sign table to solve this inequality. So we write x minus 2, we write x plus 3, and we write the overall fraction. Now we solve each factor equal to 0. So we try x minus 2 equals to 0, we get x equals to 2. And we do x plus 3 equals to 0, we get x equals to -3. So we write these numbers in our sign table. And on the right, infinity, on the left, -infinity. So x minus 2, we agree that it is 0 when x equals to 2. Any value greater than 2, let's say 3, 3 minus 2 gives a positive answer. Any value less than 2 will give us a negative answer. X plus 3, we also agreed that it's 0 when x is -3. Any value greater than -3 will give a positive answer, and any value less than -3 will give a negative answer. So now, this is a sign table. We multiply negative times negative gives positive, negative times positive gives negative, and positive times positive gives positive. Now, one thing to point out is that we cannot have a denominator of 0, so x equals to -3 will cause us to write do not exist. The fraction does not exist in such a case. So let's look again at our inequality. We want it to be greater than 0. So let's shade the intervals where it is greater than 0 or positive. And since it's greater than, not greater than, or equal to, we will use open brackets. So the domain is x belongs to -infinity till -3, union 2 till infinity. Now, so we've been graphing a bit in the previous examples. So one thing to point about graphs is that graphs have an x-intercept where y is equal to 0, and a y-intercept where x is equal to 0. So in our graph here, these 2 points, this point is where y is 0, so this is an x-intercept, and this other point is where x is 0, so this is a y-intercept. So now we will do another example. Let f of x equals to square root of x plus a divided by x squared plus 7x plus 12. So we would like to find the domain, x-intercepts, and the y-intercepts. First of all, we start by simplifying. Numerator stays the same. Denominator becomes x plus 3 times x plus 4, because the two numbers 3 and 4, if we multiply them, we get 12. If we add them up, we get 7. Now, we have to put restrictions in order to be able to find the domain. So let's look at the numerator first. Numerator, we have a square root. So x plus 8, everything inside the square root has to be greater than or equal to 0. So x is greater than, 0. So x is greater than or equal to negative 8. Now let's look at the denominator. We have x plus 3 times x plus 4. Denominator should not be 0. So x should be different than negative 3, and x should be different than negative 4. Through these conditions, we will be able to write our domain. So maybe let's draw a number line to help us. We have negative 8, negative 4, negative 3, up to positive infinity. So we want all of this region except negative 4 and negative 3. The way to write this is x belongs to negative 8 till negative 4, union negative 4 till negative 3, union negative 3 till infinity, and as you might have noticed, I used open brackets next to negative 3 and negative 4 because I do not want them to be included in my domain. Let's move on to finding the x-intercepts and the y-intercepts. So for the x-intercept, the entire function is equal to 0, so x plus 8 divided by x plus 3 times x plus 4 is equal to 0. As I explained in a previous video, when a fraction is equal to 0, it's the numerator that's equal to 0. Denominator cannot be 0 or else the fraction does not exist. So if square root of x plus 8 is 0, to solve this expression or equation, the first thing we can do is square both sides. So now we get x plus 8 equals to 0. X is equal to negative 8, so our x-intercept is negative 8, 0. Now for our y-intercept, we need x to be 0. So we plug in x equals to 0. So we have, instead of x, we write 0 plus 8 divided by 0 plus 3 times 0 plus 4. This gives us square root of 8 divided by 3 times 4. So this is square root of 8 divided by 12. We can write square root of 8 as 2 square root of 2 divided by 12. So this can give us square root of 2 divided by 6. So our y-intercept would be 0 square root of 2 over 6. So this table is taken from the book. It includes some of the basic functions which you are expected to know how to graph. So the first function is a constant, f of x equals to b. Next we have a linear function, f of x equals to mx plus b. And then we have the quadratic, then f of x equals to x cubed, root functions, square root of x, 1 over x squared, b to the x. We have two cases, if b is greater than 1 or if b is less than 1. And then we have log base b of x. And then we have sine of x, cosine of x, and tangent of x. So this is a modified table. The actual table has some more functions, but this is some of the basic functions that you need to know. Now we will move on to transformations. So we can shift the graph. So y equals to fx plus c. Thus c shifts the graph c units upwards. Minus c shifts it c units downwards. Now if we do f of x minus c, it shifts it c units to the right. Please note that this is a negative, and yes, it does shift it to the right. F of x plus c shifts its c units to the left. This is also a table from the book, page 37. Now we will move on to an example. So if we are given f of x equals to x squared plus 6x plus 10, We know that this is a quadratic, it should look something like a parabola, but we are trying to make it a little, or sketch a little more accurate. So one thing that is good when graphing quadratics is to change the format of how this quadratic is written. First of all, what we can do is complete the square. So x squared plus 6x. And here, you know a quadratic is a squared plus 2ab plus b squared. So x is a, 2ab is 6x. So we divide both of these by 2, so ab is 3x. Now we divide both sides by a, so a is x, so 3x divided by x is 3, so b is equal to 3. Therefore, b squared equals to 3 squared equals to 9, so we want a 9 in here. So we cannot randomly add numbers, so we have to do plus 9 minus 9, and then we keep the plus 10. So x squared plus 6x plus 9 is the same as saying x plus 3 all squared, because up here this was a plus b all squared. So x plus 3 all squared is this part, and we have 10 minus 9 is plus 1. Now this looks a bit more easy to graph. So if we were to graph x squared on its own, this is how the graph would look. But we want to graph x plus 3 squared. So we move 3 units to the left. And this is x plus 3 squared. And now we would like to graph x plus 3 all squared plus 1. Plus 1 shifts it 1 unit up. So this is a sketch of how it would look. So now let's move on to our second example, f of x equals to sine of 2x. It's good to start with the graph of sine of x, where this is pi, this is 2 pi, and this point here is pi over 2. Now if we were to graph f of x equals to sine of 2x, it will have the same shape with a different period. So in such questions, if you're ever confused, it never hurts to plug in numbers on your calculator if this might help. So let's plug in pi over 2, sine of 2 pi over 2 is sine of pi, which is 0, which might be an indication that this point here is pi over 2, and this point here is pi, and this is our graph. After having done this previous example, I think it is time to look at stretches and compressions of graphs. So this was an introductory example. Now let's look at the rules. So suppose c is greater than 1. If I do y equals to c times f of x, this stretches the graph of y equals to f of x vertically by a factor of c. Just in case you don't know what this means, so if f of x equals to x squared, c times f of x is as if I'm doing 2x squared. This stretches the graph vertically by a factor of c. Now if I do 1 divided by c times f of x, 1 divided by 2x squared, this shrinks the graph of y equals to f of x vertically by a factor of c. Now let's say I want to do y equals to f times f of cx. This shrinks the graph of y equals to f of x horizontally by a factor of c. For example, if f of x equals to square root of x, doing f of c times x is as if I'm doing square root of 2x. Now if I do y equals to f of x over c, so square root of x over 2, this stretches the graph of y equals to f of x horizontally by a factor of c. And y equals to negative f of x reflects the graph of y equals to f of x about the x-axis. So if this is f of x, then the reflection will be this one about the x-axis. So if f of x equals to x squared, then the reflection is negative x squared. And y equals to f of negative x reflects the graph of y equals to f of x about the y-axis. So I'd have this to be f of x, and this is negative. This is f of negative x. Now let's look at an example. So given the graph y equals to square root of x, which I will give it to you right now, the graph of y equals to square root of x is this, where approximately here we have a point 1, 1. Given this graph, use transformations to graph y equals to square root of x minus 2, y equals to square root, and all of the square root, everything under the square root is x minus 2, y equals to negative square root of x, 2 square root of x, and square root of negative x. So let's start with the first one, square root of x minus 2. So again, this is a review of the previous page as well. So if I were to do square root of x minus 2, let's look back where we learned this. It's here I shift the graph downwards, a distance of c units downwards. So I go until, let's say this is minus 1 and this is minus 2, and I shift my graph here. Again, this is just a sketch, nothing is drawn to scale, but the point is that we shifted the starting point till -2. So we finished y equals to square root of x minus 2. Let's look at y equals to square root of x minus 2, where x minus 2 is under the square root, this one. Just to note that in this case, we have a factor of -2. In here, let's look again up. So the -2 is being done to the x. So this is f of x minus c. We shift the graph of y equals to f of x a distance of c units to the right. So let's shift it 2 units to the right. So that's 1, that's 2, and our graph is the following. So we finished y equals to square root of x minus 2. Let's look at y equals to negative square root of x. What did we say about putting a negative? Let's look here. Negative reflects the graph of y equals to f of x about the x-axis. So if this above right here is the graph of f of x, the reflection about the x-axis would be the following. So this is y equals to negative square root of x. So we finished this one. Let's look at y equals to 2 square root of x. So we are multiplying f of x by a factor of c. So we stretch the graph of y equals to f of x vertically by a factor of c. So again, I'm just approximating, I'm not drawing anything exact, but let's stretch the graph vertically. What we get is something like this. So as you can see, we stretched it vertically. This is y equals to 2 square root of x. And now we will do y equals to negative square root of x. What did we say about this in the rules when we have a negative? So y equals to f of negative x, we reflect the graph of y equals to f of x about the y-axis. So if this right here is the graph, the reflection on the y-axis will look something like this. And this is y equals to square root of negative x. Now, operations on functions. There are several operations you might do: add, multiply, divide, subtract, and another operation we'll talk about later today. So let's start. F plus minus g of x is f of x plus minus g of x. F times g of x is f of x times g of x. F divided by g of x is f of x divided by g of x. So for these first three basic operations, all you have to do if you're given a function, let's say f of x equals to 2x and g of x equals to, let's say 3x squared, all you have to do is add them up if you would like to do f plus g of x. You simply add them up, or you simply multiply them if you're asked to multiply them, or divide them. Now, one thing to note about division is that g of x should be different than 0 for this to work. And one more thing about all of these first three operations is that the domain is the intersection of the domains of f of x and g of x. So let's say in the example I gave you up here, the domains for both of them, for 2x, domain is all reals, and for 3x squared, the domain is all reals. So the intersection of both domains will still be all reals. Now let's move to composite functions. F of g of x, we can also write this way. The domain, we will look at it in an example in a minute. So let's start with that example to understand better composite functions. If we're given f of x equals to square root of x and g of x equals to square root of 2 minus x, let's find f of g. What we do to do this question is first we write f of x. Wherever we have x, we replace it by g. So I will replace x by square root of 2 minus x. This will give me, I want to simplify it using exponent rules that we learned earlier. So this is 2 minus x to the power of half. All of that to the power of half. I can multiply the exponents, which become 1 divided by 4. This is the function that I get. Now what is the domain? Keep in mind that 2 minus x has to be greater than or equal to 0, so negative x has to be greater than or equal to negative 2. And then I divide by negative 1, and when I do so, I have to flip the sign, so it becomes x is less than or equal to 2. So the domain is negative infinity till 2. Let's look at another example, g of f. Again, I write a g, and whenever I encounter an x, I write f of x in its place. So I get square root of 2 minus square root of x. In order to find the domain, one thing to keep in mind is what's inside the square root. The outer square root has to be positive, and what's inside the inner square root has to be positive. It has to be greater than or equal to 0. So let's start with the first square root. So 2 minus square root of x is greater than or equal to 0. This means I can square it. So 2 minus square root of x is greater than or equal to 0. Negative square root of x is greater than or equal to negative 2. I divide by negative 1 on each side. So square root of x is less than or equal to 2, and then I square again. So x is less than or equal to 4. That's one of the conditions I need. The other condition is the inner square root. Everything inside it has to be greater than or equal to 0. So now if I draw a number line, I have 0, 4. I need it to be above 0 and below 4. So the domain is x belongs to 0 till 4. Now, let's look at f of f. So, for f of f, first we write f, and whenever we encounter the f inside, we replace it by f. So this is our answer. So let's look, we have two square roots. Everything inside has to be positive. In our case, x has to be greater than or equal to 0. And this is the only restriction on the domain. And we can write this as x belongs to 0 till infinity. Now g of g, so we write a g whenever we encounter the x, we replace it by g. So this is what we get. Now we have an inner square root and we have all of this big square root, both of which will pose restrictions on our answer. So let's start with the inner one. 2 minus x has to be greater than or equal to 0, so negative x has to be greater than or equal to negative 2. We divide by negative 1, so we flip the sign of the inequality, so x is less than or equal to 2. Now the bigger square root, so 2 minus square root of 2 minus x has to be greater than or equal to 0. Square root of 2 minus x is less than or equal to 2. We square both sides. 2 minus x is less than or equal to 4. So negative x is less than or equal to 2. We divide by negative 1. X is greater than or equal to negative 2. Let's draw a number line. We have now negative 2 and 2, and the region is this region in between. So x belongs to negative 2 up till 2. And now let's move on to another, a slightly more trickier example. So let's look at this function, f of x equals to cos squared of x plus 9. And we would like to find functions f, g, and h such that f, big F, equals to little f of g of h. So maybe this question might be a bit tricky, but just as by looking at it, one thing we might notice that one of the functions will probably be cosine of x. But x is not what we want inside the function. We want an x plus 9. So another function might be x plus 9. So if the function that's cosine of x, if these two functions are composite functions, we will end up with a cosine x plus 9. However, cosine x plus 9 is not what we want. We want it to be cosine squared x plus 9. So we might have another function that's x squared. And if these two functions are composite functions, we will end up with cosine squared of x plus 9. Now we got our three functions. All that is left to do is to order them. F of x equals to x squared, and if g of x equals to cosine of x, and h of x equals to x plus 9, if we were to solve this, so if we were to do f of g of h, first we do g of h, which will give us cosine of x plus 9, and then we do f of cosine x plus 9, which will give us cosine squared of x plus 9. Again, this is a slightly tricky exercise. Maybe with a bit more practice, you will be able to get it easily. And the answer is this answer that I'm boxing right now. Now let's move to inverse functions. So what an inverse function is, it's a function that undoes the function. It might sound weird. We will look at a few examples to help. Now, it's only one-to-one functions that have an inverse, or if we're not looking at one-to-one functions, we will have to limit the domain, and we will look at examples like this in some of our next videos when we talk about trigonometric functions. But for now, let's try the horizontal line test to check if these functions are one-to-one. Basically, we draw a horizontal line at everywhere, but we will test it at one point. It only passes in one point. So it passes the horizontal line test, so it's one-to-one. However, let's look at the function on the right. It passes in several points in the function, so it's not one-to-one. So just to point out that when we draw the inverse of a function, the function and its inverse are symmetrical on y equals to x. And the domain of x is the range of its inverse. Also, the range of f is the domain of its inverse. So we will practice finding the inverse. Let's say we are given y equals to 4x minus 2 divided by 3x plus 4. The first step in finding the inverse is switch x and y. So basically, write x equals to 4y minus 2 divided by 3y plus 4. So switch x and y. Then solve for y. We can cross multiply 3y plus 4 times x equals to 4y minus 2. So 3yx plus 4x equals to 4y minus 2. So to solve for y, we can isolate y. In our example here, 3yx minus 4y, we put all the y's on one side and everything that's not a y on the other side. And then we factor the y. And our answer is y equals to negative 2 minus 4x divided by 3x minus 4. We can write this f prime of x equals to negative 2 minus 4x divided by 3x minus 4. And this is the inverse. Now we will look at another example. F of x equals to e to the power of x plus 1. We would like to find the inverse as well. So as we did before, we will switch the x and the y's. So I will write x equals to e to the power of y plus 1. Then I would like to solve for y. So to get rid of e, I can take ln. So ln of x equals to ln of e to the power of y plus 1. So ln of x, when I have ln of e to the power of y plus 1, this simply gives us y plus 1. So y is ln of x minus 1, and I can write this as the inverse of f of x is ln of x minus 1. So now we will learn about piecewise functions. As the name suggests, a piecewise function is a function made up of several pieces. So here we have f of x equals to half of x minus 1. 1x is less than or equal to negative 2. So we will try to graph this. So we are talking about all this region here when x is less than or equal to negative 2. So that's only a sketch, not really accurate, but it will look something like this. Because exactly this point here, when x is equal to negative 2, f of negative 2 equals to negative 2 divided by 2 minus 1, which is negative 1 minus 1, which is negative 2. Now, f of x equals to 3 when negative 2 is less than x is less than or equal to 0. Now, the reason I put an empty dot here, because we see it's less than when when negative 2 is less than x, it's not less than or equal to x, it's less than x. So negative 2 is not included, it's an empty dot. However, 0 is included. X is equal to 0 is included, we fill in the dot. Now let's continue graphing. When x is greater than 0, f of x equals to negative x squared plus 4. So let's try to graph negative x squared plus 4 on its own. First, we learned earlier that x squared is this graph. If I were to draw negative x squared, I will flip it. This is negative x squared. Now negative x squared plus 4, I shifted 4 units up. So this is my graph negative x squared plus 4. So that's how I draw it. I have 4 here. Again, it's an empty dot or empty circle because 4 is not, because x is equal to 0 is not included in here. It's just when x is greater than 0. So I draw this part of the parabola. And if I'm interested in finding this point here to make the graph more accurate, I can solve negative x squared plus 4 equals to 0. So we can write this 4 minus x squared equals to 0 if it makes our lives easier. So 2 minus x, 2 plus x equals to 0. 2 minus x equals to 0, and or 2 plus x equals to 0. X equals to 2 or x equals to negative 2. So we can see this point is x equals to 2 and this point is x equals to negative 2. So in here, this is 2, the point, x equals to 2, y equals to 0. Now often when we're asked such type of questions, the following question will be state the domain and state the range. Let's start with the domain. We can see that all points, all real numbers can exist. Because let's start from the left. Everything here, we can stretch this line more. We have a filled in dot here, even if this one is empty. So pretty much, so all of the points can exist. So the domain is all reals. Now let's look at the range. So it can go as low as negative infinity up to 4, and 4 is not included, so the range is negative infinity till 4 with open brackets. Now let's look at whether a function is increasing or decreasing. So a function is increasing if f of x2 is greater than f of x1, and decreasing if f of x2 is less than f of x1 as long as x2 is greater than x1. So for example, let's look at square root of x. Let's take x1 equals to 0, x2 equals to 1, square root of 0 is 0, square root of 1 is 1. So f of x2 is greater than f of x1, so this function is increasing. Now, it's not always good to only choose 2 points. Graphing will give us a more accurate answer. This is square root of x, and we can clearly see from the graph that it is increasing. Now let's look at 1 over x squared. Again, as I said, graphing is the best in such questions. This is how the graph for 1 over x squared looks like. So we can see that it's increasing in this first portion of the graph. So it's increasing from negative infinity till 0, and it's decreasing from 0 till infinity.